the switching modulator requires FC to at least 3 FM. If you look into the modulated waveform and draw the waveforms and then see the spectrum, how exactly it is becoming, we can see that FC should be greater than 3 FM in the case of square law modulator, and FC should be greater than 2 FM in the case of the switching modulator that we are going to have it. So if you draw the spectrums, you can clearly observe how the carrier frequency should be for each of the modulators that we are going to have it. Then we have seen the detection of the signal. So we have seen what you call the analog detector, which detects the envelope of the modulated signal that is coming in for this as the input to the circuit. So we are going to follow the modulating signal envelope of your modulated signal, which is corresponds to when you pass through a filter that gives you your baseband signal M of t that we are going to have it. And there we have the time constant RC, the resistance and capacitance combination that we are going to have it along with your resistor, the diode, which is going to be our nonlinear device that we are going to have it. So for that one, we require this should be much less than 1 over FM, where FM is the maximum frequency content of our baseband signal. And the other limit that we are going to have it is 1 over FC, where FC is our carrier frequency that we are going to have it. So given the carrier frequency and the baseband signal, that is the modulated signal FM, then we can fix this time constant RC, and accordingly you can design your envelope detector circuit so that it is operating and giving you the required output after the low pass filter, so that the required detection process of your signal is coming, and we are going to get back our baseband signal M of t that we are going to have it. The other modulation technique that we are going to discuss is going to be the square law modulator. So we have seen envelope detector. Then we are going to have what you call a square law detector. Like what you have for the square law modulator, we have your square law detector. And here again, we are going to use the diode as a nonlinear element that we are going to have it. And let us assume that this is going to be having a response between the input and output as a second order nonlinearity y equal to k x square. The second order nonlinearity we are going to consider for the device, nonlinear device that we are going to have it. So that will be having. So if you plot this input output characteristics of your nonlinear device, then we are going to have a nonlinearity like this. So let us say that we are fixing an operating point or some center point as O. So onto this O, we are giving the baseband signal, the modulated signal that is coming in, so that if the point varies toward the right side and the input may be varying toward the left side, the variation that we are going to have it for both positive and negative will not be the same that we are going to have it as the output. Because when you give this the modulated signal that we are going to have it, this is what the AM signal that we are going to have it with the baseband and the carrier frequency that we are going to have it. So that we are applying to the nonlinear device with this as the center output that we are going to have it. So when there is no output, this will be the constant DC signal that we are going to have it. No input, output is constant, whereas as the input signal is going to vary, the variations in the If the input signal is going to be positive, then the variation in the output is going to be much higher compared to the variations in the negative cycle that we are going to have of the input signal. So we are having larger variations in the positive variations of the input, whereas lesser variations in the negative signal that we are going to have it here. Therefore, if we take an average of the signal, then we will be getting a waveform like this, which is nothing but our m of t that we are going to have it. So what we are doing is, to this non-linear device operating at a point O, we are giving as the input to vary towards the positive and negative direction that we are going to have it. And the output that we are going to have, because non-linearity, the positive variations in input gives you much higher variations, whereas the negative variations will be reduced. Therefore, when you take the average value of the output that we are going to have it, so actually if you plot this, the variations will be larger in the case of positive and less in the case of negative waveform that we are going to have it. Therefore, we are taking an average time. So how much time we are going to take? So this average time is a small period of your baseband signal and larger number of carrier frequency cycles that we are going to have it. That means you are having this baseband signal, which is going to be a low frequency signal. Therefore, we are taking a part of this as a time average signal. And during this part of the time average signal, we are having more number of carrier cycles that we are going to have it. So that when you take the average value, then they are going to get nothing but our baseband signal that we are going to have it. Therefore, what should be our analytical part that we are going to have it? So we are having VIM of t that we are getting is going to be, this is what your modulated signal with a baseband signal m of t, and this we are giving as an input to our non-linear device. What should be our x value? So let us say that this is some A0 is the value that we are going to have it from this point to the O that we are going to have it. This, if you say that this is A0, so A0 plus the VIM signal we are giving as input to your non-linear device. Therefore, the x value is equal to A0 plus VIM of t. So this we are giving as input to this non-linear device, which is having the characteristics of y equal to kx square. Therefore, your output signal y will be equal to A0 plus cos omega ct square into constant k. So what will be the output we are going to get out of this? So we are going to get k0 square, which is a DC signal, plus 2k A0 AC into 1 plus mt cos omega ct. And this is a DSP signal centered around your omega c plus AC square 1 plus m square t plus 2m of t into cos square omega ct. I am just squaring that x square value. X we are squaring it. So that this is the output that I am going to get. And what should be the components that we are going to have it? This is the DC signal and this is the modulated signal centered around omega c. And what is that we want after the output of the signal? The baseband signal m of t. So that we want to eliminate all the high frequency components. And this cos square omega ct gives you 1 plus cos omega ct by 2. That means 1 DC term and cos omega c. So when you multiply with cos omega c, this one, s square is 1 plus 2 mt plus m square t. You are getting only a central frequency at 2 omega c. So if you pass this to a low pass filter, the cos omega c term, and in this cos omega c term will be lost. And what is that we are going to have it remaining? So this AC square 1 plus m square t into 2 m of t into 1 by 2. Plus this k a naught square. If you pass through a low pass filter, this omega c and 2 omega c terms will be eliminated. So this is the output that we are going to have it. Suppose this you couple to a capacitor, what will happen? The DC term will be lost. You can eliminate this DC term by coupling through a capacitor, because capacitor cannot pass the DC signal. Therefore, the remaining term that we are going to have it will be m square t plus 2 mt. What is that we require? M of t only. But whereas we have this square also. So if this m square t is much less than this 2 m of t, then this m square t can be reduced or neglected. So that only we will be having m of t, which is going to be required baseband signal that we are going to have it. So what should be constrained on m of t? Therefore, if m of t is much less than 2, then your square law detector will be able to give the output as m of t only, because m square t can be neglected. So your square law detector gives the baseband signal m of t, provided this m of t magnitude is much less than 2 that we are going to have it. So this is what our square law detector that we are going to have it. The other one is the third demodeling circuit that we are given or named when we are discussing is the rectifier detector. So we have this rectifier detector wherein the diode we are operating as a rectifier. What is a rectifier? For positive cycles is give the output, for negative cycles the output is 0. That means it is a switching action that we are going to have it on and off. Therefore, m of t rectifier detector that we are going to have it. Then you have a low pass filter. Then you connect to a capacitor to eliminate, and this will be our V naught of t, which is nothing, will be nothing but your m of t. So this diode, we are saying that this is operating as a rectifier, or it gives for positive cycles it is conducting, and for negative cycles It is open. No output. So what is the input that we are giving? We are giving input as the amplitude modulated signal. And here for clarity I am putting the number of cycles of the carrier is less, but in practice the number of cycles will be much more in this time variation that we are going to have it. So this is the input that we are giving. And the diode is going to on only for the positive cycles. That means this input we are multiplying with a square signal. Whose frequency is the carrier frequency. The time period is 1 over fc that we are going to have it. So we are multiplying this Vam of t with the pulse signal P of t that we are going to have. So what happens? What should be the output across this resistor? Across this resistor, we are only having the positive part of your input signal. What is the spectrum of your input signal Vam of t? We have at fc and minus fc, we have the DSP signal, the AM signal with carrier at fc and minus fc, and the signal that we are going to have it. So this we are multiplying with the pulse signal. What will be the spectrum of this pulse signal? So this signal will be having at fc, 2fc, 3fc and so on at the different harmonics of the signal. So this will be having the spectrum like this. This is P of f and this is Vam of f. The spectrum of your amplitude modulated signal and the spectrum of the pulse signal. What is that we are doing? We are multiplying in the time domain Vam of t with the P of t. So what is the spectrum? The convolution of these two, AM signal spectrum and the pulse signal spectrum. Therefore, the output of this spectrum will be like this, with reduced amplitudes, because we are convolving. This we are passing through a low pass filter, eliminating all the higher harmonic frequencies of omega c, 2 omega c, 3 omega c and so on, except at the baseband centered around 0, we are passing through our low pass filter. And by bundling with a capacitor, this term also will be eliminated, so that we'll be getting only the required baseband signal that we are going to have it. So if you look into this analytical part that we are going to have it, we are having AC into 1 plus m of t cos omega ct is the amplitude modulated signal. This we are multiplying it P of t. So if you expand this into our Fourier series expansion that we are going to have it, then that will be equal to 4 by pi sigma n minus 1 by 2n minus 1 cos omega c. Therefore, when we pass to a low pass filter, the output that we are going to have it is AC by pi into 1 plus mt. Remaining higher harmonic frequencies are going to be eliminated by this low pass filter. When you pass this to a capacitor, then this will be AC by pi into m of t. Even the DC term also is eliminated, so that we are getting only the required baseband signal that we are going to have it. Right? So this is how we will be recover the required baseband signal from an amplitude modulated signal. So we will be having analog detector or a rectifier detector that we are going to have it. Therefore, now we know how to generate the AM signal by using either square law modulator or a switching modulator, and we can detect the signal by using an envelope detector, a square law detector, or a rectifier detector that we are going to have. So different techniques you can apply depending on the requirement or the availability of the devices that we are going to have it. Okay, so that is what your amplitude modulation and demodulation that we are going to have it. In here, when we are talking about the power relations, we said that the maximum modulation index we have put equal to 1, and then we said that 30% is going to be sideband power and remaining power is the carrier power. So what should be the variation of this m value? What can be the maximum value that you can allow to change the amplitude of the carrier in accordance with the instantaneous signal of your baseband signal? Therefore, what should be the maximum allowable modulation? Maximum allowable modulation index, or how much percentage you can have. Suppose if you have m of t is like this and a carrier that we are going to have it with AC, and this is AM. Okay, this is cos omega m of t, and this is AC cos omega ct. Where AC is larger than AM value that we are going to have it. So when we have this m, that is modulation index is less than 1, what is that we are having? AC into 1 plus m cos omega m of t into cos omega ct. This is what our single tone amplitude modulated signal, where m is the modulation index that we are going to have it. So when m is less than 1, the waveform will be looking like this. Whereas if m is greater than 1, the output will be there will be a phase reversal here and the zero crossing. This is m less than 1 and this is m greater than 1. Now we want to use this signal at the detection point by using envelope detector or a QLR detector. And use this to get your output using an envelope detector. What will be the output? You are going to follow this waveform, charging and discharging. Similarly, your rectified diode also, rectified direction also gives you along with this waveform, that AC by P into 1 plus MT that we have taken. So this will be the output based on your baseband signal. So there is not any problem when they are detecting the baseband signal when m is less than 1. But suppose if m is greater than 1, what is the output? You are going to have so the output is going to be following the waveform like this. Whereas it is having both positive and negative expressions as your baseband signal. But whereas your output is going to be having only the positive variations that we are going to have it. Because when it is your baseband signal is crossing negative, then the phase reversal occurs in the modulation, then you are going to get only the positive cycle. Therefore, we are not getting the exact baseband signal. If m is greater than 1. Therefore, m should be less than 1 or at the maximum when m equal to 1, then it may be having a crossing here at the origin that we are going to have it. So the maximum allowable modulation that you can have it theoretically is going to be m equal to 1 or 100%. If more than 100%, the distortion is going to come when you have your detection process. So we will not allow in the AM the modulation index to be more than 100% or m equal to 1. In practice, this will be much less that we are going to have it. We will not use this in this 100%. It's only theoretically we say that it is going to 100%. When we are talking about receivers, we say that this should be maximum of 70% only. But in practice, we are going to have 30 to 50% modulation index that we are going to have it, depending on the baseband signal. So this is how you have the allowable modulation index that we are going to have it. Theoretically, we can say it is going to be 100% modulation you can allow. Whereas in practice, the limitation is going to be 70% and actual modulation indexes are going to be much less compared to these values that we are going to have it. Anyhow, we'll see that what should be the limitations on the modulation index at the transmitting end when we are discussing about the receiver circuits. Okay. So this is about your amplitude modulation and limitations on the allowable index and what are the different modulations and demodulations that we are going to have. How you have to modulate and how we have to demodulate an amplitude modulated signal that we are going to have. Okay. So in the amplitude modulation signal, what is the bandwidth that is required? Bandwidth that is required 2 FM, because we are going to have both the lower side band and the upper side band along with a carrier also. So we have, if you have a single tone modulation, you are going to have 3 spectral lines in each side of positive frequencies and negative frequencies, and 1 carrier line at FC and FC plus FM and FC minus FM. Similar negative of these frequency components and the negative frequency, so that you will be getting the required cos omega Ct and cos omega C plus omega mt and cos omega C minus omega mt. So these are the 3 spectral lines that we are going to have it. So this is what your amplitude modulation, generation and the detection that we are going to have. Now we'll see the variations of this amplitude modulation. When we are talking about the power relations, we said that the efficiency of your modulation is m square t, mean square average value of m of t by 1 plus average value of the mean square value. M square t by 1 plus m square t. If you have only the single tone signal with m cos omega m of t, then this eta is going to be m square by 2 plus m square, because m cos omega t mt mean square is m square by 2. So m square by 2 by 1 plus m square t by 2. So that gives you m square by 2 plus m square. And you have seen that the maximum allowable m value that we are going to have it is 1. So when that be the case, your eta value is equal to 1 by 3 only. That means 33% only the efficiency that we are going to get out of this modulation, AM modulation that we are going to have it. And as you said that 33% is there in the carrier, in the sideband, and 67% is in the carrier signal. And we are saying that this carrier doesn't contain any information. The information is only omega c minus omega m or omega c plus omega m. Cos omega ct doesn't contain any information at all. Your baseband signal is present only in the 2 side band frequencies that we are going to have it. Therefore, it is a waste of transmitting this carrier power. But to transmit that, we said that we require a carrier. That's what we started with the modulation. The need for modulation. We require a higher frequency compared to our baseband signal. That's why we are having a frequency translation of your omega m to omega c plus omega m on omega c minus transmit only 33% of the power. Suppose if you have an AM signal with 1 kilowatt, out of this 67% is a waste. Suppose if you have another transmitter with that 333 watts of power and have only the side bands, no carrier, that means you are going to have 100% efficiency of the power that we are going to have it, because the entire power contains the information about the modulating signal, because you are suppressing the entire with the carrier. 333 kilowatts without carrier gives the same sideband power level that we are going to have at the receiving end, and your entire information is only in the sidebands, so it is enough to have say that you can get 100% efficiency by having only transmitting the sideband power, whereas if you transmit with the carrier, the efficiency is only 30%, right? So this we are reducing or suppressing the entire thing, and then transmitting only the two sidebands that we are going to have it. So what is that we are going to get? We are going to get a double sideband suppressed carrier system that we are going to have it. AM also is having sideband, two sideband, double sideband, but carrier is present. Whereas if you suppress that, we are going to get a DSP SC modulation that we are going to have it, which gives you 100% efficiency, power efficiency in the transmission that we are going to have it. So what is that we are doing? We are going to suppress the carrier from your AM signal. So what is that we are doing? So we are having an AM signal cos omega Ct. So having carrier and the sideband powers. Now we are suppressing this carrier. This one we are removing the carrier AC into cos omega Ct. Therefore, what is the output we are getting? AC M of T into cos omega Ct. What that we are doing? We are multiplying the baseband signal with the carrier signal. So what that we are doing here? We are discussing about your baseband signal with a carrier signal. Then the frequency is shifted instead of at zero frequency, center frequency, the frequency shifted to FC. A frequency translation that we are going to have. Therefore, your DSP-SC is a simple frequency translation of your baseband signal from zero center frequency to FC as the center frequency that we are going to have it, and no carrier power that we are going. That is impulse at the frequency FC is not available in the modulated spectrum that we are going to have it. So if you say that again, you have so we have this so this is the baseband spectrum and this is the modulated spectrum, and no carrier. There is no impulse at the center frequency FC. So we have the frequencies FC plus FM and FC minus FM. So the band frequencies FC to FC plus FM is the upper frequencies. From FC to FC plus FM, they are the frequencies from 0 to FM. In the baseband signal spectrum, 0 to FM, the positive frequencies are shifted to FC plus FM. Therefore, this we call it as the upper sideband, USB. The upper sideband that we are going to have it. Whereas 0 to minus Fm is translated as Fc minus Fm to Fc or Fc to Fc minus Fm, which are calling as the lower sideband. Therefore, we are having the total spectrum from Fc minus Fm to Fc plus Fm. Therefore, the bandwidth is again 2 Fm, like our AM signal. For negative frequencies minus Fc, we are having the relation of the negative of these spectral lines that we are going to have it. So this is what your DSPSC spectrum that we are going to have it with upper sideband and the lower sideband that we are going to have it. And here the upper sideband, if you say that it is a single tone frequency, we are having cos omega c plus omega mt. The LSB is going to be having cos omega c minus omega mt. Both these sidebands contains omega m, right? Both these sidebands contains the baseband signal m of t, omega m of t. Therefore, one sideband is enough for getting back our original signal. That's what we'll see when we are talking about the single sideband transmission that we are going to have it. Okay? So for the time being, let us restrict to a DSP signal and a suppressor carrier. When you say simply DSP, it is going to be normally we refer to AM signal. When you say SC also is added, that's only no carrier signal that we are going to have it. So always write DSP SC to represent that no carrier that we are going to have it. Okay? So this is what the transformation or the frequency translation from 0 to FM to Fc minus Fm to Fc plus Fm that we are going to have. So this is what the DSP SC signal that we are going to have it. So what is that? We want to have it. So we are going to have it, the baseband signal m of t and carrier signal cos omega ct. These two are multiplying. How to multiply these two signals? So we require a nonlinear device to multiply this signal, right? M of t and cos omega ct. That we are going to have it. Like what I have done in the case of amplitude modulation, your diode, we have taken as a nonlinear device and then obtained the modulation. Any device, when they are giving as input, we are giving m of t and cos omega ct. And what is the output we are getting? Cos omega c minus omega m and cos omega c plus omega m. Your cos omega ct is not there in the output. And 0 to Fm also is not there in the output. That means both the inputs are not reflected in the output. But any physical device, when you give the input, along with other components, the input signal also will be present. Right? For any physical device, suppose if you say that you give that input, normally we say that the second order harmonic, second order linearity will be AV1 plus AV1 square. The basic signal AV1 also is going to be the input signal. That means for any device that we are going to have it, we are going to have the input signals and the product signals also. That means if you give to a simple product modulator multiplier that we are going to have it, the output will be consisting of m of t, cos omega ct and the product m of t into cos omega ct. That is your cos omega c minus omega m and cos omega c plus omega m of t. But we have to suppress both these signals, the baseband signal and the carrier signal. How to reduce the baseband signal? How you will reduce the baseband signal? How do you reduce the baseband signal? This is the one. So this is the baseband signal. How we eliminate the baseband signal? By passing through a band pass filter centered around FC, so that this baseband signal will be eliminated. That means after this two input signals that we are going to give it to multiplier, if you pass through a band pass filter, then this baseband signal is eliminated, so that only the frequency component centered around FC and minus FC will be available. In addition to our product, now we are having the carrier frequency also. Therefore, we have to suppress this carrier frequency also. That's why we are saying that we are having what we call a balanced modulator, which balances out your carrier frequency. That we are going to have it. So instead of a simple multiplier, m of t into IC cos omega ct, you can say a multiplier. But multiplier will be having the baseband signal and the carrier signal also. But anyhow, the baseband signal can be eliminated by using a tuned circuit, a band pass filter. But still we are going to have this cos omega ct. Therefore, we want to go for a balanced modulator to eliminate this carrier also. Right? So what are the different techniques of generating your DSPSE signal that we are going to have it? So before going into the generation, what we'll be having is, when we multiply the signals, we are saying m of t. So this is the balanced modulator that we are going to have it. A generation of DSPSE signal. So we are having two amplitude modulators. For one modulator we are giving m of t, and another one we are giving minus m of t. The inverse of the m of t that we are going to have it. With the same carrier frequency SC cos omega ct. Therefore, the output of first modulator is going to be S1 of t, which we are putting as AC into 1 plus KMT cos omega ct or 2 by fct. And because we are giving minus m of t, instead of 1 plus S2 of t will be having AC into 1 minus Km of t. So output of these two modulators are given S1 of t and S2 of t. So these two are added here with the combination of plus and minus. S1 of t is plus, S2 of t is again inverse, so that minus S2 of t is there. So the output of this adder, we are subtracting S of t equal to S1 of t minus S2 of t. When you subtract these two in this adder, then what is the output? S of t equal to 2k m of t into cos 2 pi fct. That means you have only m of t and multiply with carrier without any carrier present in the spectrum that we are going to have it. That means you have balanced out this cos omega ct by having this subtraction for both the signals that we are going to have it. So what is the output that we are going to have? We are having required m of t into cos omega ct that we are going to have it. Okay? So this is what the double-sided suppressive carrier generation using a balanced modulator. That's why we say that the block diagonal that we are going to have it is m of t is one input, cos omega ct is another input. You have a balanced modulator, and output is going to be your S of t, which is going to be the product of m of t and cos omega ct that we are going to have it. Okay? Because you know how to generate amplitude modulated signal. So we have amplitude modulators. You may be having a scalar modulator or a ring modulator, anything that we are going to have it. So 2 amplitude modulators we are going to have it. Then have a balancing to give you the required DSP-SC signal that we are going to have. The next generation that we are going to have it is a ring modulator. A ring modulator that we are going to have it. The second generation method of DSP-SC is ring modulator. So we are having a circuit D1, D2, D3, D4. Or when you start with A, B, C, D to A, we are having a ring all pointing to the same direction. A to B, B to C, C to D and D to A. It is a ring. That's why we call this as a ring modulator. All pointing to the same direction when you start up to the close. And we are giving the baseband signal, the modulation signal here, and this carrier signal of the carrier frequency FC, we are giving a square signal. So this carrier signal magnitude is got much larger than your baseband signal, or on and off of these diodes D1 to D4 are controlled by this square wave signal. Your switching of the diodes is controlled by the square wave signal. And you have two center tap transformers. The first transformer secondary and the second transformer primary. So when you have this square wave signal positive on one side, so D1 and D3 are powered biased. And square wave signal is such that at A you are having a positive A and C, right? Because sine wave, the square wave we are having a positive signal that we are going to have it. When A and C are positive, this other point in the center tap transformer will be negative. Therefore, B and D will be negative. So A and C are positive and B and D are negative. So what will happen? D1 and D3 are conducting and D2 and D4 are reverse bias or open circuit. That means what are the input that we are giving modulated signal M of t is coming as the output with this switching. Whereas if the square wave signal is negative at A and C and positive at B and D, when you have square wave negative signal, then what will happen? D1 and D3 will be reverse bias. At D2 and D4 will be power bias. So that the output will be with a multiplication of -1. When this C of t is greater than 0, output is multiplied with +1. And when C of t is less than 0, we are having a cross coupling because of this D2 and D4. And you are having a multiplication of -1. Right? That's what the variation that we are going to have it with the M of t. M of t is multiplied with the +1 when C of t is greater than 0, and M of t is multiplied with -1 when C of t is negative. So that's what you have the circuit diagram that we are going to have modified with when C of t is greater than 0, you have the first one. D1 and D3 are forward bias. Whereas when C of t is negative, then you have D1 and D3 are reverse bias. So you have the negative connection. Therefore, you are having a multiplication of -1 that we are going to have it. So we are having this diodes are connecting between the input and output with multiplied with +1 and multiplied with -1, the square signal of the sinusoidal signal that we are going to have it. So we are having a baseband signal m of t, and we are giving you a square signal. So when C of t is positive, your signal is multiplied with +1, the green. And when C of t is negative, your signal is multiplied with minus. Therefore, you are having a negative part that we are going to have it. Therefore, this is what the output that we are getting at the transformer. The secondary of the second transformer that we are going to have it multiplied with m of t and the square signal that we are going to have it. So how your output will be? So what is that we are having? So we are having m of t. This we are multiplying with C of t, a square signal. So if you find out the Fourier transform of this will be 4 by pi sigma cos omega c. This will be the output that we are going to have. So what is that we are having? This we are multiplying with m of t. So this is m of t. When n is equal to 1, we are having this as 4 by pi m of t into cos omega ct plus 4 by pi when n equal to 2. What will happen? This is 2 minus 1, 1. Therefore, this is minus 4 by pi into 1 by 3 cos minus higher harmonic frequencies. So 4 by pi m of t cos omega ct minus 4 by 3 pi cos 3 omega ct. So if we pass this to a band pass filter centered around omega c, then all the higher harmonic frequencies eliminated, allowing only m of t into cos omega ct. And what is that we require? The same thing, m of t into cos omega ct. So output of this ring modulator, you tune to center frequency of fc. You are eliminating all the higher order frequency combination of 3 omega c, 5 omega c, and so on. Because we are having all the odd harmonics of cos omega c, right? And we are having only the required product modulator m of t and cos omega ct. And here, by a square wave signal with the carrier frequency omega ct. And the output, what is that we are getting? Only M of t and cos omega ct. No baseband signal and no carrier frequency also. That's why this we call it as a double balanced modulator. Double balanced modulator. Whereas previously we said balanced modulator which balances out your carrier frequency cos omega ct. By tuning this to your center frequency fc, both the frequencies, your baseband signal and carrier frequency are balanced out, and only the product of m of t and cos omega ct is available to you. That's why I am calling this as a balanced modulator. A double balanced modulator that we are going to have. Ring modulator is your double balanced modulator that we are going to have. The other one is chopper modulator. What is the chopper? Chopper. Constant AC to variable DC. Constant DC to variable AC. So conversion. So we are having a switching that we are going to have it. So this is your M of t, the baseband signal, right? The switch will be on ARC with the carrier frequency that we are going to have it. For the on period, the signal is on, the switch is on A, and for off period, the switch is on C that we are going to have it. It is chopping, cutting the signal that we are going to have it. Let us say that you have this as your baseband signal M of t, right? So when the switch is on A for a short duration, this signal is selected, like your sampling. Then for some period, the switch is on C. Then the signal again is selected, chop, and so on. Okay. And suppose if we have a signal, something like this, then what happened? The signal will be chopped like this. This we are passing through a band pass filter with center frequency Fc. What is that basically we are doing here? When we are saying that chopping, we are selecting only the which sample that we are going to have it. Remaining signal, there is no output that we are going to have it. So when the path is through a band pass filter, output will be coming something like this. But no carrier. Okay? So this we are passing through a band pass filter. Then you pass through a capacitor to eliminate output across the resistor that we are going to have it. So this is what your chopper modulator that we are going to have it. To select the product M of t and cos omega ct. So your switch is going to move with the carrier frequency. The one that we are going to have it. Basically, we can say that the typical when C of t is positive, what's going to happen? Positive and negative. So whatever input that you are going to have it is appearing across your circuit. You may say that you have a resistor also. And this resistor we are passing through a band pass filter, the output of this load across this. Switching. And C of t is less than 0. This is negative and this is positive. That means there is no connection here, or whatever input that we are going to have it is appearing across the so no output. When CT is negative, you have this open. Therefore, you are having the output. So switching on and off. Whatever we have done with the ring modulator, CT greater than 0 and less than 0. A similar operation we are getting here with the chopping. Selection of your M of t that we are going to have it. and then passing through your required band pass filter centered around Fc, we are going to get back the product m of t and cos omega ct at the output that we are going to have it. Your DSB SC signal, the chopper modulator that we are going to have it. So we have seen the different generation methods of DSB SC signal. Your balanced modulator, ring modulator, or a chopper modulator. But how to detect the signal? We want to get back the baseband signal. What is that we have done in the modulation? We have multiplied your baseband signal with the carrier frequency omega ct, translated from 0 center frequency to Fc as the center frequency. Now what is that we want to do to get back the original signal from center frequency Fc? We have to transform this to center frequency 0, so that you are getting your baseband signal. That means we are doing another frequency translation. In the modulation, we are transforming or translating from 0 to Fc. And the demodulation, we have to convert from Fc to 0 frequency that we are going to have it. What is that we are going to have it? We have to multiply again with cos omega ct. Suppose if you say that mt cos omega ct is your baseband signal, or the input signal, that is we are going to have it for your demodulator. Mt cos omega ct is your input signal to your detector. This is centered around Fc. This we have to convert into a frequency centered around 0. That means a frequency translation we are doing. How we are doing frequency translation? By multiplying the input signal with a carrier frequency. And now for this, what is the input signal? Mt cos omega ct. That we multiply with a cos omega ct. It should give back your baseband signal with some other frequencies also. Next slide. So what is that we are doing? We are having the modulated signal S of t. That is mt cos omega ct. That we are having a local oscillator as a receiver, which are saying AC cos omega ct plus phi, because the same phase may not be available at the receiver. Cos omega ct is the required frequency that we want it, but exactly as the transmitter, when we are receiving the signal, we don't know what is the carrier frequency phase. Therefore, we are separating as if some variation is there in the phase. For the time being, we are assuming that omega c is the same. Okay? So when we multiply these two with the product modulator, what is that we are going to get? S of t into C of t that we are going to have it. So we have and cos omega ct plus phi. So this is the product that we are having in the product modulator. And we know how to have your product modulator. The same your ring modulator or any circuit that we are going to have it. So we have the mt cos omega ct is your st, and cos omega ct plus phi is the local oscillator frequency signal that we are going to have it. So what is that we are doing? We are multiplying. So when I multiply cos omega ct and cos A and cos B. Therefore, what is that you are going to have it? Cos A minus B and cos A plus B. That way I am going to have it. So A minus B cos omega ct plus phi minus omega ct gives you cos phi. M of t, AC also we have to put. So AC by 2, M of t cos phi, that way I am going to have it. Then we are having A plus B. A plus B is cos 2 omega ct plus phi. Okay? You have A minus B and A plus B. A is omega ct plus phi, B is omega ct. So difference is cos phi and the summation is 2 omega ct plus phi. So this if you pass through a low pass filter, what will happen? This cos 2 omega ct will be eliminated. That's what the block diagram that we have seen. After product modulator, we are putting a low pass filter. So that this cos 2 omega ct is going to be removed. What is that we are remaining? And mt into cos phi. What is that we require? What is that we require? M of t only. So cos phi is the additional term that we are going to have. If cos phi is 0, phi is 0, there is no phase difference between your input signal and the Laplace phase that we are going to have it. Then your output is going to be M of t only. But phi if it is going to change, because we are having oscillator which generates the phase with different times, it is going to increase or decrease phi value. Therefore, your M of t will be having a variation in the amplitudes. Not only your base time signal M of t, but because you are multiplying with cos phi. So there will be a shift in the amplitudes, increasing and decreasing. Right? But if suppose phi equal to pi by 2, what will happen? The value will be 0. Cos phi by 2 is 0. Therefore, output is going to be 0. So when we have this pi equal to plus or minus pi by 2, then output is going to be 0. This we call it as a quadrature null effect. Because we are having a quadrature phase variation that we are going to have it, and output is going to be 0. So we have to have a 0 phase so that there will not be any distortions in the baseband signal that we are going to have it. Therefore, we require what we call a coherent detection that we are going to have it. So we have to generate a coherent carrier, that is in phase carrier, like that of your transmitted carrier frequency phase that we are going to have it. So even though you say that you have you know the transmitted carrier cos omega ct plus some phi, the same we are going to have it local oscillator, but during transmission the distance is there, time that we are going to elapse it, therefore phase is going to change. Therefore, we have to use this received signal to generate a coherent carrier. Different carrier generation techniques are there to generate a coherent carrier. Suppose the frequency that we are generating at the carrier is not the same. That's what I put as the second condition, cos omega ct, actually delta omega ct. Delta has been shifted and now pasting. Right? So the carrier that we are going to generate is cos omega ct plus delta omega ct. So what is the output? M of t into cos delta omega ct. Right? Therefore, the output after this passing through a low pass filter is M of t into cos omega ct. For the timing I am assuming pi to be 0. Okay? Previously we have considered phi is a varying value. Now we are saying the carrier is a varying frequency, phi being the same. So what does it mean? Delta omega ct is very, very small, delta value. That means your baseband signal, instead of appearing like this, this is delta omega c or delta fc. As if that we are having moderated by delta fc, a shift in the spectrum that we are going to have it. It will not be the same signal that we are going to have it, moderated by this delta fc. If delta fc is larger, then you may be having again. So this is delta fc and this is minus delta fc. Even this because you can't have a variation that we are going to have it, and at the maximum this delta fc may be allowed a maximum of 30 Hz. So there are some variations you may be having. But anyhow, we will be having a feedback network to stabilize this carrier frequency also in the coherent generation of the carrier signal that we are going to have it. So one carrier generation to avoid this frequency So this is what one way of generating your carrier signal that we are going to have it. So what is that we are having? We are having m of t cos omega ct. Right? That we are squaring. So m of t cos omega ct square. So what is the output that we are going to have it? M square t cos square omega. Cos square omega ct. So what is that we are having? Cos square omega ct, DC term plus cos 2 omega ct. So that we are having a filter to filter out this 2fc. The DC term also is eliminated except that second harmonic frequency, the remaining components are eliminated by squaring this. Then have a divider to get your cos omega ct. So what are the input phase that we are going to have it? The same will be continued with what are the frequency variations that we are going to have it. This frequency will use it as a localized frequency that we are given in the previous block schematic. That means instead of generating a carrier frequency at the receiver, we are using the input signal itself to generate your carrier, and this carrier is naturally in phase and incoherent with your received carrier frequency that we are going to have it. Therefore, whatever the quadrature null effect and the frequency variation that we have seen can be eliminated by going for this coherent carrier generator that we are going to have. So this is how we will be using the carrier coherent carrier generation, so that the phase and frequency variations of your localized generator can be reduced. Because if we have a separate generator, what are the design that we are going to have it, you will not have the same carrier frequency or the same phase that we are going to have it. No doubt you have designed exactly at the transmitter and receiver the same carrier generator. But as the time goes, the aging of the different parameters of the transmitter and receiver will not be the same. Therefore, again, the variations will be coming. Therefore, we should have a coherent carrier generator. That's what we are doing here by squaring, division, and then we are going to get your required frequency that we are going to have, cos omega ct. The same phase and the same frequency that we are going to have. The other demodulation of your DSP signal is what we call post-pass receiver. We are having a post-pass loop, post-pass receiver. The block schematic of this post-pass receiver is this. In this we have an in-phase channel and a quadrature channel. In-phase channel and quadrature channel. I channel and Q channel. So what is that we are doing? We are having a DSPSC signal. Not using a power splitter, you are giving it to two balanced modulators. For which, for one, we are giving cos omega ct, and another one we are giving sin omega ct. Right? 9 degrees phase shifter we are using. So one we are giving cos omega ct, and another one we are giving sin omega ct. So what is the output of these two? After low pass filter, you are going to have 1 by 2 AC cos phi m of t. When you have a phase control oscillator that we are going to have. This is the local generator that we are going to have it. A VCO we are using to generate the required frequency, and we are assuming that initially that it is cos omega ct plus phi. A phase angle variation is there. So in the second quadrature phase, you are having sin phi into m of t. So we are having two outputs. One multiplied with cos phi and another one multiplied with sin phi. Suppose phi is 0. That is exactly our voltage control on VCO is generating the same phase signal. What will happen to the quadrature output? It is 0. And the in-phase channel is going to be having cos phi is 0. Therefore, we are having cos m of t. That is half m of t that we are going to have it. Therefore, we are getting our required signal. If phi is 0. Suppose phi is not 0. So sin phi signal is there and cos phi is there. So we are having a 9 degrees phase shift between these two signals. So these two signals are given to a phase detector to give you corresponding DC output. So that DC output is going to control the phase of your voltage controlled oscillator. So let us say we have pi 1 less than phi. So we have still a variation. Then again, you are giving it to your loop, the other that we are going to have it. So cos phi and sin phi 1. So these two signals will be compared and a corresponding DC signal is generated until you are having the same voltage control oscillator, the same phase that we are going to have it. So we are having a cosmos loop that we are going to have it here to generate the required carrier signal, cos omega ct. Right? So the output that we are going to have it when the VCO is going to be having the same phase controlled by your phase detector output, then we are going to get back your required baseband signal m of t. The required baseband signal. Here we don't require any coherent generator because it itself is generating. The VCO is generating the required coherent phase signal that we are going to have it because of the additional circuit that we are going to provide with the circuit. Previous circuit we said that it's only a modulator frequency translation we are going to give, but phase is going to change. Therefore, you require a coherent generator. So that is the additional circuit that we are going to have. Whereas here we require additional balanced modulator, phase detector also, along with your normal local oscillator generator that we are going to have. This VCO is your local oscillator. In the previous block that we are representing as a local oscillator. Okay? So this is how your post transistor operates and gives you the baseband signal M of t without any quadrational effect or variations, increase and decrease of your M of t depending on your pi value. So that can be eliminated by using your post transistor. In addition to this, we'll be having here we are having M of t and cos omega ct. The bandwidth that we are having is 2 FM. But whereas only one signal we are transmitting, M of t. And we know that we can differentiate between cos omega ct and sin omega ct quadrature. Therefore, one signal M1 of t we will multiply with cos omega ct, and another signal M2 of t you multiply with sin omega ct, the same carrier. But one thing is, phase is going to be difference by pi by 2, sin omega ct and cos omega ct. But the bandwidth of these two is the same, because mt into sin omega having a quadrature phase. That's why we saw that quadrature multiplexing signal that we are going to have it, so that we can have two signals, M1 of t and M2 of t, and we are having a cos omega ct with a 90 degree phase shift to generate your quadrature phase signal, that is a cos of sin omega ct. So these two are combined and transmitted. Even though they are having the same bandwidth, we can separate out at the receiving end without any mixing of these two signals that we are going to have it. So we are having 2 FM as the bandwidth, but now we are having two signals with the same bandwidth. That means for signal you are having only FM as the bandwidth. Right? So by going for a quadrature multiplexing, we are using the same bandwidth 2 FM to transmit two signals. And how to generate the signal? So we have the multiplex signal. Then if you multiply the cos omega ct, so cos square omega ct will be there. Right? So what is the output you are getting? The input that we are going to have it is M1 of t cos omega ct plus M2 of t sin omega ct. So this we are multiplying with cos omega ct. So M1 of t cos square omega ct. Therefore we are having 1 plus cos 2 omega ct. Right? So I can pass this to a low pass filter and cos 2 omega ct can be eliminated. Whether sin 2a. So 2 omega ct we are having. No DC term here. Therefore, when you pass to a band pass filter, cos omega ct corresponds to this, and second harmonic corresponds to this. Entire thing eliminated except this M1 of t by 2 will be there as the output. Okay? You multiply with cos omega ct and pass to a low pass filter. So cos omega CT terms will be eliminated, except the M1 of T by 2 will be the output that we are going to have it. Whereas if you multiply with sin omega CT, so when you pass to a low pass filter, this entire thing is eliminated, and M2 of T by 2 will be the output that we are going to have it. So both the signals we are recovering without any mixing of these two signals. And the transmitting bandwidth that we are going to use is only 2 FM. So by using the quadrature multiplexing, two signals we are multiplexing in the same bandwidth. That's what we multiplex when we are saying that transmitting in the same bandwidth. So two signals, 2 FM only we are using. That means per signal we can say that bandwidth is half only. Multiplexing, you can transmit twice that of the signals that we are going to have to compare to our AMR DSP with the same bandwidth. So that's what the advantage by going for a quadrature multiplexing signals that we are going to have. So that is about your DSP SE generation and detection and increasing the number of signals by going for a quadrature multiplexing. Okay, I think we'll stop here and we'll meet again in the new year. So wish you all a happy new year in advance.